Hello, this is Peter Newman. I'm answering a question on the Ansys innovation space on elastic plastic limit load. I've already answered the elastic limit load in this post, so I'm answering question 2 here, internal pressure to cause gross yielding with plasticity. And here's my answer to the first question on the elastic limit load, and that is simply to put a unit pressure of 1 megapascal, solve that with a linear model, get the stress from that, which was 9.2, and take the tensile strength of 250, divide by that stress to get the pressure that would get you to that elastic strength, tensile strength value. So we're going to start with this model, and we're going to turn it into a nonlinear model to get the plastic limit load. So here is that model, and the steps that we need to go through to make it nonlinear is to go to engineering data and grab from the plasticity toolbox, say bilinear is the simplest plasticity model, and always be careful of the units when you type any numbers into this. 250 megapascals is a lot more than 250 pascals. 0 is the tangent modulus, which means as soon as you reach the tensile strength, no additional stress will develop. And that is a conservative result. Here, just refresh the project to bring that material update into mechanical. And now we are looking at the model with that material. The next thing to turn it into a nonlinear model is to turn large deflection on. That's something you need to do. And we also want to make this a multi-step. So we're going to use 3 steps. Step 1, that's just to get to the elastic load pressure of 27 that we got from the first analysis. But now we're going to add steps 2 and 3. So step 2 ends in 2 seconds, and I think we'll leave auto time stepping on there. Step 3 is where the fun begins. Actually, step 2 we will go with some auto time stepping because this is when plasticity is occurring, but we might not need a lot of steps to track that. Step 3 is when we want a lot of steps to track the development of the plasticity through the section. And so we'll use 100 steps, and we won't let it take anything larger. And it doesn't matter how big that is. And these are, of course, all with large deflection on. And so under the pressure, we'll go from 27 to 30 to develop some initial plasticity, and then we'll just do 1 megapascal more to get it to the fully plastic section. I've obviously solved this once before, so I had to do a few iterations to find some good numbers to demo for you today. But with that in place, we can go ahead and solve. And it doesn't take long to solve because I've used a pretty efficient mesh here. And when we go look at the force convergence plot, we'll see that we get easy iterations for step 1 and then step 2, and then we force it to take a lot of small steps, and it starts failing to converge and then ultimately cannot converge at the end. So we get an error, but that is the desired result. And what we're going to do is insert some equivalent plastic strain or equivalent total strain. There's not going to be much difference there. We'll just go with this. and we will retrieve that result. And what you see is the mesh blows up because Ansys always plots the unconverged solution, which can be helpful, but not in this case. What we're interested in is the load step just before it blew up, and that is this. So here we can see there's plastic strain through the entire section. If we go back to an earlier time, here we have no plastic strain in the outer fibers, and maybe here at the end of step 2, retrieve that result. We've got plastic strain going through most of the section, and then maybe somewhere in here there's just a few elements left that have not yet got to the fully plastic state. So depending on your definition, retrieve this result. You could call that the fully plastic state. We'll also increase the scale here a little bit. You could call that the fully plastic state, or the limit load when the unit just completely fails is here. So that is the methodology to create a fully plastic state, and depending on what you want to use for your definition, if you think, let's say, this result, be one less. I'll just take the last point as being an easy one to get to, 2.72. If we define that as the fully plastic failure load, how much pressure is that? If you recall, in step 2, we were at 30 megapascals, and at step 3, we were at 31. So we added just 1. And the solution failed at 2.72, or 0.72 of the way through that last 1 megapascal added on to 30. So the answer for the failure pressure for complete failure is 30.72, based on how much time into the last step of 1 megapascal we were at. So that's my answer to the question. Hope you enjoyed the video. Thanks. Bye.